transfer function is given by this. So hence the characteristic equation will become 1 plus gs hs, and this will be equals to 1 plus k over s plus 1 s plus 3 and s plus 5. Now let's start making the starting point of the root locus. As we all know, the root locus starts with the open loopholes, and for the given transfer function we don't have any zeros over here, and we have three open loopholes placed at -1, -3 and -5. So for this, the starting point will be on the S-plane. Three poles are placed at -1, -3 and -5. Let's say this is going towards infinite, this minus infinite, plus infinite. Now let's start taking the, as we have discussed in the previous section, of the root locus on real axis. And now it is very much clear that this segment will be the part of the root locus, and this going towards the infinite will be the part of the root locus, and all the three loci terminates towards the zeros. All these three poles, or the three locus originating from these three poles, will go towards or will end towards the zeros of the transfer function. But as it is pretty much clear from the given transfer function, there is no physically placed zeros for this open loop transfer function. So now this says again, by the given rule, all the three loci definitely will go towards the zeros of the transfer function, but all the three zeros of this transfer function is placed at infinite. So this also gives us one more rule for the root locus, but let's first discuss this one. So the direction of the loci is very much important, and as we know, this pole or the loci originating from this pole will go towards the infinite on the real axis, and we assume that 1 0 is placed at infinite on this real axis. Now there is no other place to move. This segment is not part of a root locus. This segment is also not part of the root locus. So this pole surely is going towards this one direction, and this is going towards this one. So whenever we have this kind of a scenario, the two poles moving towards each other, so definitely they will meet at some point between this section -1 and -3, and then they will break away at some point between this section, and they will move towards, or they will break in a different loci or separate loci, and they will, and each loci will move accordingly. So it is a pretty straightforward rule. To find out the breakaway point, we always take dk by ds is equals to 0. So when we find the root of this, we get the breakaway point. Now let's take one more example to show how dk by ds, or how your breakaway points can be identified. Now let's take one more open loophole over here. Sorry, one more open loop transfer function having three poles placed at 0, -1 and -2. And characteristic equation will become 1 plus gs hs. And from here, three poles are located at 0, -1 and -2. And root loci on real axis will be this segment will be part of the root locus, and between these two poles, this segment will be part of the root locus on real axis. And this loci is going towards the infinite, and these two poles are converging towards each other, and definitely they will have the breakaway point between -1 and 0. Let's find out the breakaway point for the given transfer function. dk by ds is equals to 0. So let's first find out. So for the given transfer function, find out the k from here. So from here, your k will be equals to, from this characteristic equation, 1 plus gshs equals to 0, and your k will be equals to minus of s plus 1 s plus 2. How does it come? The characteristic equation will be this: 1 plus k over s into s plus 1 s plus 2 equals to 0 from this, and from here your k will be equals to minus of s into s plus 1 and s plus 2, and from here your k will be equals to s cube 3s square plus 2s, and the rule is dk by ds is equals to 0. So let's differentiate this equation, and we get dk by ds is equals to minus of 3s square plus 6s plus 2, and this equation puts equals to 0. Now let's find out the root of this equation, and this equation gives us the root dk by ds is equals to 0, gives us the two roots is equals to minus 0.426 and minus 1.574. So it gives us two root. Now let's again come back to the root locus over here. As we know, the breakaway point exists between 0 and minus 1. So this point cannot be a breakaway point because at minus 1.5 somewhere here, this point is not part of the root locus. So this cannot be breakaway point. So definitely 0.4226 is going to be the breakaway point. So after getting the breakaway point, since taking root locus on a big going towards the infinite, because there is no physical zero given in the pole, in the transfer function. So all the three poles are going towards the zero which exist on the infinite. So this is going towards infinite, and they will break away from here. They will go towards infinite, and to check whenever we have any loci or any loci originating from pole going towards the infinite, so those loci will go towards the infinite with respect to some angle which is known as asymptotes or asymptotic angles, and all these angle will be starting from some point which is on the real axis, which is known as centroid. So this gives the origin of the next rule of the root locus, which is finding the centroid and asymptotic angles. Let's first discuss the rule to find out the centroid. So here I'm just directly giving you the formula by which we can find out the centroid to draw the asymptotic angles for the root locus. And centroid is find out by denoting it minus of sigma equals to summation real part of open loop poles minus summation real part of n divided by minus n, where n is the number of open loop poles and m is number of open loop zeros. So this is the formula to find out the centroid. Here the real part of the open loop poles is nothing but, if we just again take the transfer function, the given transfer function, open loop transfer function, which is k over s into s plus 1 into s plus 2. So there is definitely no open loop 0 given in the transfer function, and we have only three open loop poles for the given transfer function placed at 0, minus 1 and minus 2. So summation of open loop poles will be 0, minus 1 and minus 2. It will be like this. From this formula, sigma A will be summation, as it is given over here, real part of the open loop poles. So we have three poles over here. So summation. So one pole is at 0, the minus 0, and other pole is at minus 1, and the third pole is at minus 2, and minus real part of the open loop pole, and there is no 0. So we don't have any 0 over here, and divided by minus number of poles minus number of 0. We have three poles, open loop poles, and we don't have any physical 0 for the given transfer function. So n minus m will become 3, because here we have three poles for the given transfer function, and we have 0 zeros for the given transfer function. So this will become 3, and from here the centroid, the value of centroid will become minus 1. So here this is your centroid from where we are going to draw the asymptotic angles. Now let's see the formula for the find out the asymptotic angles, and formula to out the asymptotic angles is the asymptotes for the any particular root looking for the given transfer function can be found by using this formula: 2q plus 1 180 divided by 3, where q is from 0, 1. Here 3 instead of 3, because the given transfer function gives us n minus m is 3. So the formula, instead of 3, it is 2q plus 1 180 divided by n minus m. And for the given transfer function, n minus m value is 3. So I'm directly finding out the value of asymptotes for the given transfer function, and this will become 2q plus 1 180 divided by 3, and putting 0 q is equals to 0 1 2 3, and it goes up to n minus m minus 1. So for the given transfer function, n minus m value is 3 and minus 1. So for the given transfer function, q will vary from 0 and it will go up to 2. So this is the exit formula is 2q plus 1 into 180 degree divided by minus m, where q varies from 0, 1, 2, and it goes up to n minus m minus 1. So that's why for the transfer function, the q will vary from 0 to up to 2. So asymptotic angles for the given transfer function will be, put q is equals to 0 and will have 180 divided by 3, 60 degree. Put q is equals to 1, will have 180 into 3 divided by 3, so 180 degree. And put q is equals to 2, and we'll have the third asymptotic angles placed at. Now let's, keeping in these three angles in the mind, now let's again draw the root locus. So we have 1 0, one pole at 0, one pole at minus 1, and one pole at minus 2. By taking first rule, root locus on the real axis, this segment is part of the root locus and going towards C when it's infinite. This is also part of the root locus, and both the poles are converging towards each other, and they will have the breakaway point at minus 4.426. So they are going to break away from this point, and we have centroid placed at minus 1. From here we are going to draw the three angles, the asymptotic angles. So first one is 60 degree, the other one is 180 degree, and the third one is 300 degree. So these three asymptotic angles we have drawn over here. So asymptotic angles we draw because we need to find out the three loci which is going towards the infinite. They should go along with the asymptotic angles. Now here we can see this asymptotic angles having the angle of 180 degree, and this particular root loci originating from minus 2 pole is already going towards infinite along with this asymptotic angles. And from here these two loci will break away and they will go towards the infinite along with these asymptotic angles. They will go towards the infinite. So this is the root locus for the given transfer function. Now here we can see the root locus or the loci going towards the infinite along with these asymptotic angles will definitely cross the imaginary axis and will get entered in the positive half of the plane. So now we need to find out at which point they cuts the imaginary axis and at what value of k the poles are getting entered in the positive half of the S-plane. And now this gives the origin for the next rule of our root locus, and which is root locus on imaginary axis, at which point they cut the imaginary axis. And for this one, now let's take directly, as we know, we have already studied about the Raoult-Hurwitz array. I'm directly going to apply the application of the Raoult-Hurwitz array to find out the imaginary point cut or the root locus cutting on the imaginary axis. So the characteristic equation for the given transfer function will become s into s plus 1 s plus 2 plus k equals to 0. This is a characteristic equation. Further simplification will give s cube plus 3s square plus 2s plus equals to 0. And the considering Raoult-Hurwitz array with respect to this equation will be s cube s square s1 s0. The first entry will be 1 and 2. The other entry will be 3 and k. This entry will be 6 minus k divided by 3, and this will be the k. And as We know for all the roots of the characteristic equation to lie to the left of the image axis, the following condition should be met. From this Rutherford's array, the condition is coming that your k should be greater than 0 coming from here, and the other condition is 6 minus k divided by 3 should be greater than 0. And if this value, the critical value of k, which corresponds to the location of roots on imaginary axis, is 6 from here, this value of k makes all coefficient of this row is 0, because if let's say k is equals to, so this will become 0. So one value we have identified, at k is equals to 6, the loci will be on the imaginary axis, and beyond the k equals to 6, your loci will get entered into the positive half of the plane. And to find out at which value they are cutting the imaginary axis, now let's form the auxiliary equation, because if this row becomes equals to 0 when k is equals to 6, row auxiliary equation will become equals to, from here, 3s square plus k equals to 0.